Welcome to Unit 4. In this unit, we'll be taking the derivatives we learned how to compute in the last unit and trying to figure out what they actually mean in a number of different contexts. At the end of the unit, we'll look at a fairly traditional numerical method that's also based on derivatives. We'll start with a quick derivative review though. So imagine you have the graph of y equals 2 sine of 5x plus 3. What's the slope at x equals pi over 4? So this is a classic derivative question. If we're looking for the slope on a graph at a single point, we're basically asking what is the derivative? i.e., what is dy dx at x equals 3? Pi over 4. Well, let's calculate the general formula, and we use our chain rule ideas here. We have 2 sine of 5x. The derivative of sine anything is cos of the same thing, times the derivative of the inside. So we take the sine, differentiate it, and then we multiply by the derivative of the inside, which is 5, and the derivative of a constant by itself being added like that is simply 0. So we can tidy that up, bring the 5 out front, and we'll have 10 cos of 5x. That's the general formula for the slope of this graph at any point. And if we're interested specifically at the point x equals pi over 4, then dy dx will equal 10 cos of 5 times pi over 4. And if you reach for your calculator, you'll find out that the value of cosine of 5 pi over 4 will be negative 1 over root 2, or if you like, around negative 0.707. And so this would turn out to be 10 times that, or approximately negative 7.07. That would be the slope at x equals pi over 4. All right, let's do another example, again just for practice of the derivative rules. On the graph of x equals 14 e to the minus t minus 3t, at what rate is x changing at t equals 2? Now please be careful. What we're talking about here is a graph where x is the dependent variable and t is the input. So x is the output, t is the input. So unlike the last example where x was the input and y was the output, we're going to take a slightly different derivative here. What we're going to want is dx dt. And if we calculate the derivative, dx dt, or if you like, x prime of t, then we can use our rules for the derivative of an exponential. It's always the same thing, but then times the derivative of the inside, which would be negative 1 in this case, minus the derivative of 3t, and that's simply 3. And so we can call that minus 3 minus 14 e to the negative t. Now again, we want to evaluate that at a particular point, so we just sub in the value t equals 2. So x prime of 2 is minus 3 minus 14 e to the negative, there's our t, e to the negative 2. So we can demonstrate pretty easily how to calculate the slope values for a graph at a certain point using the derivative rules we've learned. Now let's talk about interpretation of these values. So for example, consider the statement, I am walking at 1.2 meters per second, fairly reasonable travel speed. From this, we would make some predictions. One prediction might be, well, how far do we expect to travel in the next second? Well, we'd expect to travel 1.2 meters. Why would we say that? Well, we're thinking we're traveling 1.2 meters per second and we're doing it for 1 second, so it wouldn't be unreasonable to say 1.2 meters will be the total distance. Likewise, if we were asked how far do we expect to travel in the next 2 seconds, well, one way to think of this is every second we travel 1.2 meters, 1.2 meters for every second. And so if we travel for 2 seconds, we expect to travel 2 times that 1.2 meters per second. All right. And again, units work out nicely here because we have 2 seconds, the interval, times our 1.2 meters per second, and we get 2.4 meters. Fairly straightforward. What about a third of a second? Well, we see the pattern already, right? We're going to take our time interval, 1/3 of a second, multiply that by our speed, and we're going to get 1/3 of that, which would be 0.4 meters. Let's clean that up a little bit. There. So from this walking speed and adding in some idea of time interval, we can get a distance. Anyone who's taken physics, this shouldn't be a huge shock, but it's important to recognize that this is a derivative value, and we're going from a derivative to a change in the original function, which is our position function. Just for one last example here, if we walk for 10 minutes, well, we'd have 1.2 meters per second times how long is 10 minutes? Well, our rates are in seconds, so we'd have 10 minutes, and get the units right, there are 60 seconds per minute. That's a nice way to arrange the canceling of values. There's 60 seconds per minute. Minutes cancel, seconds cancel, and we end up with 1.2 times 600, and that gives us 720 meters in the next 10 minutes. Okay, so that's not a bad analysis. It's worth noting something important about those values, though. These are all going to be approximations. So we have to keep that in mind. In particular, we expect some to be more accurate predictions than others. What we just said is, let's imagine our time points here of 1/3 of a second, 1 second, 2 seconds. Here's time. Here's position. We've been relying on the velocity being 1.2, or our speed being 1.2 meters per second. So position in meters, time in seconds. If we follow that curve, what we've been basically doing is forecasting into the future based on the information we have about the time now. If we go up to 600 seconds, what we might expect is, well, we might be going faster, we might be going slower. There's a lot of time between now and 10 minutes from now that might affect how fast we walk. However, in the next 1/3 of a second, short of running into a brick wall, we're probably going pretty close to this same velocity, the same speed. So we expect the most accurate prediction on our last page. Won't be guaranteed, but we expect the most accurate to be associated with the shortest time interval. There we go. We expect it to be associated with the shortest time interval. When we do the calculations in general, of course, we're saying we think, barring any other information coming in, that the velocity we have now is going to be similar to the velocity we experience over the time period in question. So we expect our speed of 1.2 meters per second, or the derivative of position, to be roughly constant. Over each time interval. And whether that's true or not depends on the scenario. And the truth of it will dictate how accurate those predictions we made were. Let's take a different example in mind for a second. Let's let R be a function of A, be the monthly revenue. So revenue R for a company, given advertising spending of $A per month. In fact, actually, sorry, A thousands of dollars per month. So our function takes in advertising, thousands in advertising, and then through F, we get thousands in revenue. Okay. What kind of interpretation can we make of statements like this then? F prime of 200 is equal to 1.8. Well, again, this is a derivative. So it's the derivative. A better way to write it here might be dr dA. And this is thousands of dollars in revenue divided by thousands of dollars, thousands in revenue, thousands in advertising. So the input is when A equals 200, what are the dollars? 1,000, what are the units? They're in thousands of dollars in advertising. The 1.8 is the ratio of consequence for each new, let's put it this way, for each additional 1,000 in advertising, we expect, or we will get, 1.8 thousand $1.8 in revenue. The 1.8 means for every increase in our input in the advertising, we expect to get 1.8 times that in revenue back. Let's put that into practice and see if that helps settle it in. So let's take that example where we have $200,000 in advertising currently, and we're going to increase the advertising spending by $2,000. Okay, we said that f prime of 200 was equal to 1.8, and based on the logic in our last thing of dollars revenue per dollar of advertising in thousands. So the units are not quite as nice here, but they're workable. Then if we increase our spending by $2,000, well, each 1,000 in advertising gets us 1.8 in revenue. So if we multiply, or if we increase our ad by 2,000, gave it away, we're going to have a net increase of 1.8 times 2 thousands, let's put it in words, thousands in revenue. And again, we could put extra units in here of this is 1.8 revenue per advertising, and this is $2,000 in advertising, so the units cancel again, and we get back to thousands in revenue. This might be a little new for a lot of students, especially if you haven't done sort of a business stream, but hopefully the ideas are intuitive enough and concrete enough that this is making sense. If not, think back to the earlier example and just try to draw the parallels with speed and position. All right. Likewise, if we increase the advertising by 1 million, so not a measly 2,000, but we went to 1 million, what would we expect our revenue increase to be? Well, same approach exactly. We take that 1.8 times 1,000 thousands, that's better known as 1 million, and we'd expect that increase in revenue. Now, of course, we don't think this is going to necessarily be very accurate. So let's make a comment about that. Not likely accurate. And this is how big budgets get blown. We see something at a small scale and think, wow, if we could just expand that to a much larger scale, we would be great. And underlying those assumptions is typically something our brains do naturally, which is assume that things are roughly linear. If I double my input, I'm going to double my output effect. And once you get into crazy regimes like this of 1 million relative to 200,000, it's probably not true. In the terms of calculus and functions, it's not true or not likely to be true because the scale of the increase in input is very large. And our derivative information is about very small changes. So if we make a big change, we can't really trust the derivative calculation to be particularly accurate on this scale. Let's do a little interpretation here. Just one last bit on this particular example for the moment. If our advertising budget is $200,000 and we are told that, based on studies, based on our data coming back from the field, that the rate of response of advertising at that level to revenue is 0.8. So in other words, we get 0.8 thousand in revenue for every 1,000 in ads. Should you spend more or less next month? Let you think about that for a second. Okay. My argument would be definitely not. Not if this is 0.8. And why? If we increase ad spending, let's make it by a tiny amount. Let's make it by $1. We're going to get an increase in revenue of $0.8. Well, that sounds pretty good. We just increased our revenue. Except it cost us $1 to do that. We spent $1 and we got 80 cents back. That does not sound like such a great deal anymore. So it's very possible to have rates that are positive, but depending on what the units are, and the fact that these are dollars going in and dollars going out, you might actually need different rates, like rates above 1 would be good in this case here. This rate we had initially, where we said the rate was 1.8, that means each $1,000 spent in advertising gets us $1.8 back in revenue. So we're covering our expenses. One of those dollars is what we spent on ads, and the 0.8 is profit, or additional profit. Here, we're not even making back our money because we haven't hit a rate of ad spending to revenue that goes above 1. So just an interesting sideline for these kinds of things, and some of the ideas that people get about derivatives being positive or negative being the most crucial thing. Sometimes the scale of them matters even more. All right, a couple of quick concept questions just to see how things are going. A chemical reaction consumes reactant at a rate given by a function. So the C here in the input is the amount of catalyst. So the C is for catalyst. F of C is given in moles per second. So there's some idea of a rate. If we know the catalyst level in milligrams, we can find out the rate of some reaction in moles per second. Okay. What would the units of the derivative f prime of C be? I'll give you a couple seconds to think about that and then go through it. Okay. Just remember, whatever this graph looks like, when we talk about the derivative, f prime of C is going to be a slope. And as soon as we say a slope, the units of that slope are going to be the units of moles per second divided by milligrams. For each milligram of catalyst, what effect on moles per second will we have? So moles per second per milligram change in the catalyst present. And that gives us moles per second milligrams. It doesn't make as much sense in this form as it does in this form, but we could write it out this way if it made sense in some other context. All right. Here's another question. If the derivative, keeping that in mind, the units can be a real guide here. The units of f prime for a catalyst level of 10 milligrams is equal to negative 0.2. which of the following statements would be true? I'd say pause the video, read those over, and then we'll look at it. Okay. Adding more catalyst to the 10 milligrams present will speed up the reaction. Well, again, let's think about what we have here. We have our catalyst, and we have that is in milligrams. We have the rate in moles per second. And what we just said is, if we had 10 milligrams present, the slope of the relationship between these two things would be negative 0.2 slope. I don't know what the graph does before, I don't know what the graph does afterwards, but it's negative 0.2 slope right here. And what that tells you immediately is that if you increase the amount of catalyst, what's going to happen as a result? You're going to get a decrease in rate. So if we add more catalyst to the 10 milligrams already present, so it's local around that, we will slow down the reaction, decreased rate. Absolutely. So B is definitely correct. Is it the only correct thing is the other thing we should check. What if we went the other way and decreased the amount of catalyst? Well, that brings us up back this way on the curve. If we decrease the amount of catalyst and this slope is correct, we'd be moving back up the curve, and in fact that would lead to a speed up in the reaction or an increase in the rate. So in this case here, that derivative tells us two things. That derivative being negative tells us two things. That if we increase the catalyst, we'll decrease the rate. But it's also possible in this particular scenario that we could decrease the catalyst and that would move us the other direction up the curve and result in an increase in the reaction rate.